Assalamualaikum and hello everyone. I'm Cikgu Hasnita from SMK Baganjaya, Butterworth, Penang. This is Physics Form 4 for DLP classes. And in this video, I'm going to discuss with you the second content standard on Kepler's Law, Part 2. So before we proceed, let us do some recap on what we have learned previously. So do you remember we have discussed the first three laws in the first learning standard? Do you remember them? Yes, very good. The first law states that all planets in the solar system move in an elliptical orbit with the sun at one of its focus. It's the Lu from the Lula Look song. Very good. And the second law? Yes, it says that a line that connects a planet to the sun sweeps out any equal areas in an equal time. La. What about the third law? Yes, the third law states that the square of the orbital period of any planet in the solar system is directly proportional to the cube of its orbital radius, where t squared directly proportional to r cubed. It's the loop. So remember our song, Lu la lu la lu la lu, very well. Alright students, so if you are ready and good to go, without further ado, let us begin with our discussion on the second learning standard on how to express Kepler's third law where t squared directly proportional to r cubed. So in order to formulating Kepler's third law, first and foremost, you must understand that yes, all planets in the solar system makes a circular motion around the sun. And this Kepler's third law, it can be formulated by using the combination of Newton's universal law of gravitation, if you remember we learned in the first content standard, and also the concept of circular motion, which involve, yes, centripetal force. So when we equalize these two equations, this is what we are going to get. So on the left is the, yes, formula for centripetal force where F equal mv squared divide r. And on the right is the formula for Newton's universal law of gravitation where G mm divide r squared, sorry. The capital M is mass for the sun, yes, and the small m is in the mass of the planets which evolving the sun. All right, so from here we can cancel both sides with m and r, and this is what it will become, v squared equal gm divide r. Okay, and then from here this v can be substituted to 2 pi r divide t. Do you remember what is this equation for? Very good, it is linear speed. Okay, linear speed is 2 pi r divide t. So we substitute v, so this is what we get. Okay, 4 pi squared r squared divide t squared. Okay, then from here we place the period at one side and the radius at one side. So this is, it become, okay, on the left t squared, so on the right equal to 4 pi squared r cubed divide gm. Okay, and students, this equation can be simplified from this expression where t squared equal k r cubed, where k is a constant. Okay, 4 pi squared divide gm is a constant. So this is how we determine the Kepler's third law formula. Okay. Okay students, so I hope you're clear now on how to express the Kepler's third law formula from the combinations of the centripetal force and Newton's universal law of gravitation formula which I showed to you just now. And let us continue with the third learning standard. I think this is the most important part for you to get, where we are going to solve problems by using this Kepler's third law. Okay, so previously from Kepler's third law, we have understand that the relationship between the orbital period and the radius of the orbits is expressed in this way. T squared equal 4 pi squared r cube divide gm. And when you are comparing two planets as shown in this diagram, where we have Earth and Mars both are orbiting the Sun at their respective orbital radius r1 and r2 and their respective orbital period of t1 and t2. So this is the formula which represent Earth, okay, and this is the second formula which represent Mars. Okay, and since 4 pi squared divide gm is a constant, so later we can cancel them off. So when we divide the first formula to the second formula, this is what we are going to get. Okay, where t1 squared divide r1 cube equal to t2 squared divide rt cubed. So this is the formula you are going to apply whenever you solve a problem involving two planets involving the Sun at their respective orbital period and orbital radius. Yes. So let us take a look at this example number 1. Okay, you have the figure given here. It shows two planets. We have Earth and Mars. Both are orbiting the Sun, where given the radius of orbit of the Earth is 1.5 times 10 to the power of 11 meter, while the orbital period of the Earth and Mars is given 1 year and 1.88 years respectively. When you see the word respectively here means, okay, the first reading goes for the first planet return. So 1 year for Earth and 1.88 years for Mars. Alright? Okay, so you are asked to calculate the radius of the orbit of Mars. So how to find them? Yes, very good. We can use the Kepler's third law formula in comparing two planets. So before that, remember the 3 steps I always taught you in solving a problem involving calculation. So the first step, you have to list out all the given information. So we have R1. This is the orbital radius of the Earth. T1 is the orbital period of the Earth. T2 is, yes, orbital period of Mars. And this is what we are looking for. Okay, R2, the orbital radius of Mars. Okay, so this is the related diagram. So the second step, we determine which formula can be applied. So this is the formula we are going to use in order to find R2, where T1, R1 represent Earth, T2, R2 represent Mars. Yeah, so you just do the substitution. The third step is substitution. So we substitute in the correct place for each T1, R1, T2, and R2. And you just have to work well with your calculator. So this is the orbital radius of the Mars, where it is 2.285 times 10 to the power of 11 meter. Okay, and for the final answer, you can leave your answer from 2 to 4 decimal places. Okay, simple, right? Okay, now let's check on the second example. Okay, I hope you do this together while following this video, so it will help you to understand the content in a most better way. Okay, so we have figure here. It shows a research satellite which needs to orbit at the height of 390 kilometers from the Earth's surface. Okay, which is to capture a clear image of the Earth's surface. So the question is, what is the orbital period of the satellite? So in the first example, we are looking for the orbital radius of Mars, and here now we try to figure out what is the orbital period of this satellite. Okay, so this is another information you are given. The radius of orbit of the moon is 3.83 times 10 to the power of 8 meter. Okay, and the orbital period of the moon is 655.2 hours. So we have two objects orbiting the Earth. The first object is the moon, and the second object is the satellite, or the other way around. Okay, the first object can be the satellite and moon is the second. So again, how to do the solution? First, we list out all the given information. Okay, so here you have to be very careful. Okay, in the question, you are given the height of the planet from the surface. So in order to find the orbital radius of the satellite, you have to add with the radius of Earth. Okay, this is the radius of Earth, and this is the height of the planet from the Earth surface. So the orbital radius is count from the center of the Earth to the center of the satellite. So 6.76 times 10 times 10 6 is the orbital radius of the satellite. Okay, and R2 is the orbital radius of the moon. T2 is the orbital period of the moon. So what is the orbital period of the satellite? Okay, now the second step, we write down the formula we are going to apply. Yes. And the third step, again, substitution. Okay, so we are looking for T1. Again, make sure you place all the substitution in the correct order. And finally, this is what the answer we are going to get. So the orbital period of the satellite is 1.536 hours. Okay, simple, right? Just apply the 3 steps and you are going to come out with the correct answer. Okay, students, so I hope you can deal well with example 1 and example 2. And now let us do more practices on Kepler's third law. Alright? So the first exercise number 1, you are given this figure where it shows the orbit of planet Venus which orbiting around the Sun. So you are asked to compare the linear speed of planet Venus at its 3 positions, X, Y, and Z. So what can you say about their linear speed in all 3 positions, X, Y, and Z? Very good. So we say that the linear speed at Y is the highest and at Z is the lowest. So when we do the comparison, Y greater than X greater than Z. Very good. Okay, now let's take a look at the second question. You are asked to determine the height of a communication satellite that is orbiting the Earth with a period of 24 hours. So this is the related diagram to this question. Actually, it is quite similar with the second example if you notice. And this is another information you are given. The period of orbit of the moon, 27.3 days. And the orbital radius of the moon is 3.83 times 10 to the power of 8 meter. If you notice here, the period of the orbit of the moon are given in days, and the orbital period of the Earth is given in hours. So first, you must put them in the same units. Either you put them in hours or you put them in days. Okay, so here we are looking to the height of the communication satellite. Okay, so how to find? This is all the information given. This is the radius of orbit of satellite. It is equal to radius of Earth plus its height. So this is what we are going to find. Okay, R2 is the orbital radius of the moon. T1 is the orbital period of the planet, and T2 is the orbital period of the moon. So 24 hours is equal to 1 day. Okay, so now we have equalized the period in unit of day. So what is H? Okay, so this is again the formula we are applying in order to find the height of the satellite from the Earth surface. And we do the substitution. So T1R1 refers to the planet, refers to the satellite. T2R2 refers to the moon. Yes, very good. So just do the substitution and again work well with your calculator. So later you will find the height of the satellite from the Earth's surface is 3.587 times 10 to the power of 7 meter. Okay, so I hope you are clear and understand all the steps I show you here. Okay. So now let us continue with question 3. Again, you can see the diagram here. It shows 4 positions of planet revolving or orbiting in elliptical orbit around the Sun. So this is the Sun at one of the focus of this elliptical orbit, And we have planet A, planet B, planet C, and planet D. So the question is, at which position is the planet moving at the lowest orbital speed? Actually, this is the same planet, but they are now in a 4 different positions. Position A, position B, position C, and position D. So at which position the planet moving at the lowest orbital speed, students? So lowest orbital speed means the planet must be the furthest location from the sun. So which one? You can see the furthest position. It will definitely be very well. Okay. And now question 4. Alright. Again, this is a diagram you are given. There is a comet orbiting the sun in an elliptical orbit. Okay. The question is, the orbital speed of the comet in its orbit is, so which one is correct? Is it constant? Is it decreases when closer to the sun, or does it increases when closer to the sun? So again, remember how the linear speed changes when the comet evolving the sun. Yes, very good. So the answer is C. The linear speed increases when it is closer to the sun. Okay, students, so are you still doing good there? Very good. Okay, now let us continue with question 5. Okay, so you are given 3 statements here, and which statement is correct about Kepler's second law? So the first statement, the orbit of a planet around the sun is an ellipse with the sun at one focus. Second, the square of the orbital period of any planet is directly proportional to the cube of the radius of its orbit. And C, a line drawn from a planet to the sun sweeps over equal areas in an equal time interval. So how do you memorize Kepler's law? Remember our Lula Loop song? Lula, 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 loop. So Kepler's second law, law of area. So which one tells us law of area? Definitely the answer is yes, very well. C, a line drawn from a planet to the sun sweeps over equal area in an equal time. The answer for A refers to, yes, Kepler's first law, okay, law of orbit. Meanwhile, for B, it is stand for Kepler's third law, the loop there. Very good. Okay, now let us continue with exercise number 6. Okay, question 6 is again a question on calculation. They give you a distance of the Earth from the Sun is L. Okay, distance mean here is the, very good, orbital radius. And we have an asteroid which is orbiting the Sun in 1/3 years. So this is the orbital period for the asteroid. The question is, what is the distance of the asteroid from the sun? So actually here we are looking for, very good, orbital radius of asteroid. So this is all the information given. R1 is L, T1 is 1 year, T2 is 0.33 years in decimal places. So we are looking for R2, again, orbital radius of asteroid. So the second step, yes, the equation. T1 R1 refers to the Earth and T2 R2 refers to the asteroid. Yes. And the third step, we do the substitution. So the period, orbital period of the Earth is 1 year and its orbital radius is L. And for the asteroid, this is the orbital period, 0.333. Don't forget the square and cube there. Okay, so we are looking for R2. So when you solve this equation, so R2 is equal to 0.48 L in terms of L. Okay, very simple, right? Very good. Okay, now let's proceed with our final exercises in this discussion. Exercise question number 7. Okay, question 7, they give you the distance of a planet from the sun is 9.6 times of the distance of the Earth from the sun. Okay, the question is, what is the orbital period of the planet in years? Okay, so how to solve this? Any idea? It sounds difficult, but actually it is not. We just apply the same formula where this is all the given information. So we took R1 as Z. Okay, actually you can use any letters, any unknown. Alright, and T1 is given 1. Okay, T1 we know is the orbital period of Earth, which is 1 year. And R2 is 9.6 Z. In this question, they tell you that the distance of the planet from the sun is 9.6 times, which means 9.6 times further, okay, than the distance of the Earth from the sun. So we took the distance of the Earth from the sun as Z, which means R2 is 9.6 Z. Okay, so I hope you're clear with that. So this is what we are looking for, the orbital period of the planet. Okay, so second, we just apply the same formula. So T1 R1 goes for the Earth, and T2 R2 goes for the planet, the second planet. Okay, and this is the substitution. 1 year is the orbital period of year, and Z is the orbital radius of Earth. Okay, the distance. So this is T2. Okay, then the answer will be, so we cancel off a Z here as shown, which means T2 is 29.745 years. Alright, simple, right? Okay, so students, I guess that's all to do for the second part of Kepler's Law. So I hope you have tried to do all the exercises I've discussed in this video. There are 7 of them altogether plus 2 examples. I think it's enough for you to understand Kepler's Law very well. And don't forget to do more exercises to familiar yourself with the formula. Okay, so what's going to happen next? I will see you again in our next lesson. It will be on Content Standard 3.3, the final content standard in this chapter, main satellite. So till then, again, thank you very much for following this video. So I hope it benefits you, and take a good care of yourself. See you again soon. Assalamualaikum, and have a pleasant day ahead.